All right, today we're diving into a really fascinating paper that tackles a huge challenge for building intelligent agents. The question is this: how can a world model learn to predict cause and effect when its only training data is a massive, unlabeled pile of in-the-wild videos from the internet? This research proposes a pretty clever way to unlock the potential of these unstructured datasets.
So here's our roadmap. We'll kick things off by defining the core problem, what's called the action label bottleneck. Then we'll get into the weeds of how the paper learns from this messy, unstructured video, the novel methods they use to regulate information, and how they actually test the actions they've learned. And finally, we'll see how it all comes together for downstream planning tasks before wrapping up with the key takeaways.
Okay, so let's start with the foundational premise here. For an agent to reason, to plan, to do anything intelligent, really, it absolutely has to be able to predict the future. Specifically, it needs to predict the consequences of its own actions. That is the entire job of a world model.
But there's a huge catch. Most world models need explicit action labels. They need to be told this was action A, this was action B. Getting those labels is incredibly expensive and time-consuming at scale. And this dependency creates a massive bottleneck. It means we can't tap into these gigantic, diverse datasets like YouTube Temporal 1B, which is a real shame because that's where all the rich, real-world visual data lives.
And this brings us right to the heart of the paper's argument. If we want to build a truly general and transferable world model, we have to move beyond our clean, curated, task-specific data. We have to embrace the complexity, the noise, and the sheer opportunity of in-the-wild video.
This slide really breaks down the difference. On one hand, you have curated data from games or robotics. You know the agent, its body, its embodiment. You have a nice, limited set of actions, and the environment is pretty clean. On the other hand, in the wild data is the complete opposite. There's no single agent. The action space is practically infinite. You've got people walking, cars driving, cats jumping, and the environmental noise is through the roof. This is a whole new ballgame in terms of research challenges.
So, how do the authors actually tackle this mess? They propose what they call a latent action model, or LAM. Now, this model has two key parts that are learned together: an inverse dynamics model and a forward model.
So here's the high-level view. The inverse dynamics model is kind of like a detective. It looks at the past frame and the future frame and has to infer the latent action, basically a vector that explains the change between them. Then, and this is the crucial part, that latent action is regularized to control how much information it contains before it's fed into the forward world model, which then uses it to predict what happens next.
Now, if you're thinking carefully about this setup, you might spot a potential problem. There's a risk of a causal leak. If the inverse model gets to peek at the future to infer an action, what's to stop the latent action vector from just cheating? It could just encode the entire next frame, which will let the model make perfect predictions without ever learning anything meaningful about actions at all. It would just be a compression trick. To solve this exact problem, the authors look into 3 different techniques to regulate or put a bottleneck on the information content of that latent action. First up is sparsity, using an L1 norm to encourage the model to use only a few dimensions of the action vector. Second is adding noise, which is a classic VAE-style trick that just makes it harder to reliably encode too much information. And third is discretization through vector quantization, which has been a pretty common approach in other work. And you can really see the difference these approaches make. On the left, using a sparse, continuous action, the model does a great job predicting the complex motion of a person walking into the frame. But look at the right. The discrete quantized action really struggles here, and the prediction is just this blurry, indistinct blob. The numbers tell the same story. This chart shows the prediction error, so lower is better. You can see how the performance of the sparse and noisy models changes as you give them more capacity. They can adapt to the complexity. But the discrete model is stuck with a consistently high error. It just doesn't seem to have what it takes to scale up for these rich, in-the-wild videos.
Okay, so the evidence is pointing towards these continuous, regularized actions being better. But that opens up a much deeper question. What are these actions actually learning? Are they just a statistical quirk, or do they represent something meaningful? And, most importantly, do they generalize? This takes us to how the paper evaluates the properties of these learned actions.
So this leads to a really critical research question. If your model is trained on videos without any consistent agent, no single robot, no single video game character, what do the actions it learns even mean? And could you take an action learned from one video and successfully apply it to a completely different one? Well, it turns out the answer is a resounding yes, and the results are pretty amazing. In this example, the model looks at a man walking to the left and figures out the latent action for that. Then they take that exact same action vector and apply it to a totally different video of a flying ball. And what happens? The ball starts moving to the left. This is a really powerful demonstration of transferability.
Now, to prove this isn't a fluke, they tested quantitatively with a cycle consistency test. The idea is you take an action from video A, apply it to video B, then re-infer the action from that result and apply it back to video A. It's like a round trip. As you can see in the table, the error only goes up by a little bit, about a factor of 1.3 for the sparse model. This is strong evidence that these actions are robust and can be transferred and re-inferred reliably.
So here's the key insight. The fact that there isn't a common embodiment, a shared body, actually forces the model to learn something much more fundamental. It doesn't learn a man walks left. It learns the pixels at this location in the frame should transform and move to the left. The actions are camera relative, and that's the secret sauce that enables this kind of powerful transfer. But, the ultimate test of any world model is whether you can actually use it for planning. So now we get to the big question. Can this model, trained purely on random internet videos, actually be used to solve concrete robotics and navigation tasks? To bridge that gap between the abstract latent space and real physical actions, they train a small, lightweight controller. This controller's only job is to be a translator. It learns how to map a known, understandable action, like a specific robot arm movement, to the corresponding vector in the latent action space that the world model understands.
And look at these results on the droid robotic manipulation task. The planning error for the latent action models, especially the noisy and sparse ones, is right there, competitive with the baseline. What's so impressive about this is that the baseline model was trained on data from this very task, and it had access to the true action labels. Our model had neither, and it's still performing just as well.
And it's pretty much the same story on the recon navigation task. The models trained on in-the-wild videos put up a really strong performance. This really drives home the idea that this learned latent action space can serve as a kind of universal interface for planning across totally different tasks and embodiments.
Okay, let's wrap things up by summarizing the key contributions of this work and maybe looking ahead at what might be next.
So, in a nutshell, this work is the first to really show that learning these latent action models on huge, wild video datasets is actually feasible. It makes a strong case that continuous regularized actions are just plain better than discrete ones for this kind of complex data. It uncovered this really cool emergent property of transferable camera-relative actions. And finally, it proved that these models can act as a universal interface for planning, getting results that are competitive with models that had way more advantages.
This research definitely opens up a lot of exciting doors, but it also points to new questions. The information constraint, the bottleneck in this work, is static. It's always the same. But real-world scenes have all different levels of complexity. So a really interesting question for future work is this. What if a model could learn to dynamically adjust the capacity of its latent actions on the fly, using more information for a really complex scene and less for a simple one? That feels like a really promising direction for the next generation of world models.